Bismillahirrahmanirrahim. How are you, students? Today we will do numericals of chapter number 6, Fluid Dynamics. It's lecture number 27, page 169. Now, numerical problems. First numerical is water flows through a 1 centimeter pipe with a speed of 1 meter per second. What should be the diameter of the nozzle if the water is to emerge at 2.1 meter per second? First I will write data. I will write the data. Now, if you look to the numerical, it is water flows through a 1 centimeter diameter. So diameter at one end is 1 centimeter. So radius will be 0.5 cross 10 raised to power minus 2 centimeter. You can use centimeter units, or you want to use this unit, both can be used. Okay, now diameter pipe with a speed of 1 meter per second. Speed is what? 1 meter per second. 1 meter per second. What should be the diameter of the nozzle if the water is to emerge at 2? So we have to find d2. We have to find d2. d2 is equal to question mark, and water is to emerge at v2 velocity is 2.1 meter per second. So we have to apply the formula and sort out this numerical. Now we know that from equation of continuity, I will erase the data, you just write with yourself. According to equation of continuity, a1 v1 is equal to a2 v2. As we know that a1 is equal to pi r1 square is equal to pi r1 is equal to d1 divided by 2 whole square, and a2 is equal to pi divided by d2 divided by 2 whole square. Radius is half of diameter, so square of radius, so square of diameter. So pi d1 square divided by 4. This 2, when you take square of this 2, it will become 4, and diameter will become d1 square. v1 is equal to pi d2 square divided by 4 v2 square. Now 4 will be cancelled with 4, pi with 5, and you know the value of this, you know the value of d1, you can calculate d2. So do it. Now 6.2. In 6.2, water is flowing smoothly through a closed pipe system. At one point, speed of water is 3 meter per second. Speed of water is 3 meter per second. So data. Speed of water is 3 meter per second, while at another point 3 meter higher. Water is flowing smoothly through a closed pipe, so it will become v1 is equal to 3 meter per second, and h1 is equal to, let's say, 0. v2 is equal to, at one point speed of water is 3 meter per second, while at another point 3 meter higher the speed is 4 meter per second. at lower point the pressure is this 80 kilopascal. What will be the pressure at the upper level? So I will it's better that I will plot the diagram for you people and I will write with data. This is the two end of pipe. Let's say here H1 V1 3 meter per second at this point, height is 0. Here H2 is 4 H2 is 3 meter H2 is 3 meter and velocity at this point is V2 which is equal to 4 meter per second. Find the pressure at the upper point. Here the pressure is 80 kilopascal. In place of kilo, in place of K, we will write 10 raised to power 3. So I will write the formula, apply, you will do it. Applying Bernoulli equation, P1 plus 1 divided by 2 rho V1 square plus rho GH1 is equal to P2 plus 1 divided by 2 rho V2 square plus rho GH2. So H is given, these are constant, these are given. Density per water is 1000 kilogram per meter cube. You can find the value of P2 also. P1 is given, this is given, this is given, this is given, this is given, so do it. Now 3. An aeroplane wings is designed to date when the speed of the air across the top of the wing is 4. So let's say you will plot a simple diagram that only that it will become easy for you. Plot a diagram like this. Let's say this is some portion of the aeroplane. So speed of the air at the top wing is 450 meter per second. The speed of air below the wing, V2 is 410 meter per second. Here the speed is low, so here the pressure P2 will be high. Pressure P2 will be high and pressure P1 will be low. Because your speed is high, pressure will be low. What is the pressure difference between the top and the bottom of the wing? So we have to find P1 minus P2 question mark. We have to find P1 minus P2. We have to calculate the difference. So remember the data and I will write the numerical for you. Density of air is 1.2 kilogram. In this case you take density of air. So applying Tarsili theorems or Tarsili theorems. P1 plus or Bernoulli, you can do it with Bernoulli equation also, 1 divided by 2 rho V1 square plus rho GH1 is equal to P2 square P2 plus 1 divided by 2 rho V2 square plus rho GH1 H2. Height should be ignored. H1, the difference between H1 minus H2 is equal to 0. H1 will be equal to H2. Both are at the same height. Let's say the difference between the wing is negligible. So you drop this and this one. These will be not written. P1, you will write P1 plus 1 divided by 2 rho V1 square is equal to P2 plus 1 divided by 2 rho V2 square. Now you can do it with the help of this one. Water flows through a pipe whose internal diameter is 2 cm at a speed of this 1 meter per second. What should be the diameter of the nozzle if the water is to emerge at a speed of 4 meter per second? So applying equation of continuity, I will write first one. How much is the internal diameter of the pipe? D1 is D1 is 2 centimeter. The velocity V1 is 1 meter per second. D2 is question mark, and V2 is 4 meter per second. So pi r1 square, I will write from the beginning. A1 V1 is equal to A2 V2. Applying this equation you can do it. In place of A1 we will write pi r1 square, and r1 square is equal to d1 square divided by 4. R is equal to d by 2. Similarly, put the value of A2, you will do it. You are all in senior class, so you can do it. Water flows through a pipe whose internal diameter is 2 centimeter. Now eight equal drops. This is very important. 8 equal drops. Number of drops are 8. 8 equal drops of oil are falling through air at a steady velocity of 0.1 meter per second. So terminal velocity is 0.1 meter per second. If the drops recombines to give a single drop, before number of drops is 8, and it give you a single drop. What should be the new terminal velocity? This is initial terminal velocity. If they combine, the terminal velocity will become Vt prime. So when it recombines, I will do the verification. You just remember that the radius in first case is r, and here the radius is r prime, and here the radius is r. Let's say radius is considered to be r. It will become 2r. It will become double. When 8 droplets are combined, the radius will become double. I will do this verification. You just memorize it now, right now. The formula for this is V terminal velocity will become 2g V terminal velocity is equal to 2g rho r square divided by 9 eta, and Vt prime is equal to 2g rho r prime square divided by 9 eta. Dividing this equation, dividing equation A by equation B, so simplified, I will write the simplified form. Vt prime is equal to Vt into r2 r prime square divided by r square. Vt prime is equal to Vt r prime square divided by r square. Use this equation, you can find the value of terminal velocity. Now numerical 6. Calculate the speed of E flux. Calculate the speed of E flux. Calculate the speed of efflux of kerosene oil from a narrow hole of tank. If pressure is 4 atmospheric. Pressure is how much? Pressure is 4 atmospheric. And 1 atm is equal to atmospheric pressure. This is 1 atm pressure. 1 atm is the unit. You should convert it into Pascal. So in place of this you will write this value. Now density of kerosene oil is how much? 0.72 kilogram per meter cube. Now we have to calculate speed of efflux, and we know that V is equal to 2 multiplied by pressure divided by density. This one 1 divided by 2 pressure is equal to 1 divided by 2 rho V square. So 2p divided by rho is equal to V square. Taking square root you will get this equation. 6.7. A small sphere of volume V falling in a viscous medium acquires a terminal velocity V. What will be the terminal velocity of a sphere of same material and volume 8 times falling through the same medium? So you will write the equation for both. A sphere, look at your book and read. A small sphere of volume V. A small sphere of volume V falling in a viscous medium acquires a terminal velocity V. So terminal velocity is written like 2g rho r1 square divided by 9 eta. This is equation A. Now volume is equal to 4 divided by 3 pi r cube, and radius will become, from this you will calculate the radius. So radius from this equation, radius will be equal to 3v, 3 is multiplied there, 4 will divide by 4 pi whole power 1 by 3, because radius is radius cube, so you will take cube root. Now V terminal is equal to, remember this equation. Now V terminal is equal to, you will calculate you will simplify, and in V terminal velocity, if you look to the equation, 2g rho r1 square, 2g rho r1 square divided by 9 eta. In this you will put the value of r that we already calculated, and then simplify, you will put this value, so you will get the equation in this shape. Vt is equal to 2g rho 9 eta, so it will become 9 eta. In place of r1 you will write 3v, we calculated it previously, and 2 by 3. This value, you will get this value. Now the next is, according to a condition of the question, the new terminal velocity is equal to 8 vt. So just put the values and simplify. You will get the terminal velocity. After making simplification, you will get that Vt is equal to, you will write 8 here because it is given in the condition that the new terminal, what will be this, the terminal velocity of a sphere of same material and volume 8v. So we should calculate volume. First you will calculate volume. Volume is new volume is 8 that of previous volume. So as we know that, I am writing the equation again and again. We have calculated the terminal velocity before. That terminal velocity, I am writing again the relation 2g rho divided by 9 eta, and after this we have written 3v divided by 4 pi 2 by 3. This is per terminal velocity. So here Vt prime will be equal to 2g rho 9 eta and 3v prime 4 pi 2 by 3. We will write this in similarity. This is Vt prime and this is the value of Vt before terminal velocity, and after, when there is change in volume, when this condition is applied, it will become like this. So put the value of V in V prime, in V terminal, and calculate, simplify, and then you will get the final. After simplification you will get that Vt will become 4 times that of, when volume become 4 times, increase 4 times, the terminal velocity will increase 4 times. Now next question. I will explain this equation again. You should memorize some equation because V terminal velocity is equal to 2g rho r1 square divided by 9 eta. This is when there is no change in volume. When change in volume, Vt is equal to 2g rho r1 square. This will become prime 9 eta. We know that volume is equal to 4 divided by 3 pi r cube, r1 cube. You will calculate the value of r1 and put in this equation and simplify. When you simplify, you will get an equation in the shape like this. V terminal is equal to 2g rho 9 eta 3 cross 8v divided by 4 pi whole की power 2 by 3. You will get this value. As we know that this is per V terminal prime, you will write this one. For Vt you will write this is V prime, actually volume V prime, and V terminal per before, when there is no change in volume, Vt is equal to 2g rho 9 eta 3v divided by 4 pi 2 by 3 whole power 2 by 3. You will write this. This is before changes. When there is Change in volume Vt, terminal velocity changes. 2g rho and 9 eta will not change. 3v prime 4 pi whole power 2 by 3. In place of v prime, you will write 8v and relate with this one. You will get the answer. Now 6.8. Determine the radius of water droplet. Determine the radius of water droplet. Falling through air with a terminal velocity, this one. Terminal velocity is given. Terminal velocity is given. Density of water is given. Density of air is given. Viscosity of air is given. You will write, I will write the simple relation for you people, and you just do it by yourself. 2g rho r square divided by 9 eta. This is the equation, and we have to calculate the radius. So radius from this is equal to 9 eta Vt divided by 2g rho whole square root. Thank you, students. This is the last numerical that we have done. If you feel any difficulties, WhatsApp me, I will do that again. Thank you, students. Allah Hafiz.